next speaker is Phillipp Woefel, who will talk about weight-free, space-bounded shared memory primitives and concurrent systems.
Okay, so this is, I think, Aris has given a great introduction to this talk. Thank you very much. I'll also talk about the asynchronous shared memory system. We'll have n processes, and they perform atomic operations on shared objects. That's how they communicate. And so typical shared objects that you could have in a system is a register, which you can just read or write. Or you have a compare and swap, which stores a value. You do a compare and swap with parameters old and new. And what it does is if the old value, the old parameter matches the value of the object, then it changes it to new and returns true, so that's successful. Otherwise, it just returns false and doesn't change anything. And it also supports the read operation. Another operation that we'll talk a little bit about is a fetch and add. So a fetch and add object just stores an integer, and the fetch and add operation with parameter x just adds x to the value stored in the memory locations and returns the previous value. So those are typical shared memory operations, and in this talk I want to talk about some of the research goals that in the shared memory theory, shared memory community. So very often what we want to do is we want to see, can we implement some data structures or stronger shared memory objects from the base objects that we just assume are being provided by the system. So for example, I could ask, can I implement a fetch and add from registers and compare and swap, and how efficient is that, or a stack from fetch and add and registers. When we ask these questions, we have to talk about concurrent correctness, what correctness condition do we want, and also what progress do we want. Aris mentioned linearizability. I will go a little bit deeper into this. So the correctness condition of choice is typically linearizability. And what that means is if you have an execution, let's say here in this example on a stack, we have these push and pop operations, then what you say the execution is linearizable if you can assign every operation a point between its invocation and response, and then you order these operations by these linearization points, then the resulting execution looks like a sequential execution should look like. Right? In this case, if you order these, first the push of 1, then the push of 2, push of 3, then the first pop returns 3, and then the second pop returns 2. So this is a correct execution. And the reason why we're so interested in linearizability is because if I'm a programmer and I want to program under the assumption that all operations are atomic, then I can just instead use linearizable implementations of those operations. And the reason is these linearization points make those operations appear as if they happened instantaneously. However, this is only true for deterministic algorithms. For randomized algorithms, it doesn't work, and I'll talk about this later. Progress conditions define under what condition will a process finish its operation. The weakest is some kind of blocking progress, like deadlock freedom or something like this, and there you get only guaranteed progress if all processes keep taking steps, and obviously then one slow process can halt the entire system. Deadlock freedom is what I think was the progress condition of Aris's talk. That means as long as some processes keep taking steps, some processes are guaranteed to make progress. This doesn't block an entire system, a slow process, but it's still possible that a process starves. And in particular, we cannot really get worst case upper bounds on individual operations because a single process may never finish its operation. So what I'm interested in this talk is the strongest progress condition, which is wait freedom, and that just means every process can finish its operations completely independent of what other processes do. And in that case, we can talk about step complexity. That's just how many steps do I need to do in order to finish my operation. That's the step complexity. And that's the complexity measure that I'm interested in. And so what I'm interested in this talk is mostly linearizability and wait freedom. We'll talk about a stronger version of linearizability later. Aris has talked about how difficult it is to concurrently to manage a space in a concurrent system. These are the most famous papers that have a general technique for that. As Aris mentioned, they won the Dijkstra Award. But pretty much everything that is general is lock-free and not weight free. And I'm interested in weight freedom. So ease of integration doesn't apply to this talk, simply because we want weight freedom. And so there, about 10 years ago, we worked quite a little bit on implementing objects where we used a certain technique for reclaiming memory in a weight-free manner. And this was also later used by Blalock and Wei and for load-link store conditional, and then it just we used it again very recently in order to implement something that's called a strongly linearizable object, which is something that is applicable to randomized algorithms. And so I want to talk about this technique a little bit, and as the main example, I will use the results from this paper. And depending on how much time Kirk gives me in the end, I can talk a little bit about this recent result. So this is this result of making objects writable. And so, sometimes the definition of a shared object just doesn't support a write operation. In theory, in theoretical work, often you have something like a fetch and add. You're not allowed to write to the fetch and add object. Or for compare and swap, the way I defined it, it only allowed a read operation and a compare and swap operation, but not a write operation that unconditionally changes the value of the object. In practice, typically on an x86 architecture, all operations are allowed on a single shared memory cell. However, then you still can't write, for example, to double width objects or to multi-word registers, which are some of our main applications here. So the goal here of this work is I assume that I can at least sequentially write to the object. So sequentially I mean if I execute a write, I can change the value of the object to anything I want, as long as I don't do this concurrently with anyone else. Okay? And then what we want to do is we want to augment this with a concurrent write operation that I can overlap with other operations. This has been done in some special cases. For example, Jayanti did this for compare and swap. But our transformation is general. And it makes only the minimal system assumptions. Essentially, all we assume is that we have registers and nothing else in our system, except for obviously the sequentially writable object. And we do this, our transformation adds only constant step complexity to its overhead. So it's optimal in terms of time complexity. And it uses bounded space, and this is where the memory reclamation it's really a memory reclamation technique here. So essentially, if somebody gives you n squared sequentially writable objects, you can plug them in our transformation, and then what you get is one concurrently writable object. And it has the same step complexity as the original object, and it is weight-free. Okay? The space is n squared, where n is the number of processes. However, so ideally we would like to use less space, but we don't know how in this case. And n is a lower bound for the space. So here's an example where we can apply this. Imagine somebody gives you registers that each register can only store a single word. And I want to implement a k-word register. Okay, so I can read and write essentially to multiple registers simultaneously or linearizably. So this is what I want to implement, but all I have are single word registers. So our transformation applies to that. Why? Because I can just take k registers And by just reading them separately in independent steps and returning the sequence of values read, as long as they're only read operations, there's really no concurrent writes, so then I don't have any problem, right? So it is a k-word register. The problem is, of course, if this overlaps with some write operations. But if I assume that write operations, that I write only when nobody else is accessing those registers, then I get a sequentially writable k-word register. That's pretty trivial. And so what our transformation now does, you can take this and you get for free a concurrently writable k-word register. And in optimal step complexity, because each of those operations take only k steps, and that's the best you can do anyway. And the space is k times n squared single word registers. Yeah, so because essentially in order to implement one k-word register, I need to plug into this transformation however much space I need here times n squared. Okay, and this is k times n squared is k times n squared. So if you look at this, I need n squared of the sequentially writable objects in order to get one concurrently writable object.
That if you have n processes, then you need every object to be order of n square space. Is that a requirement, or otherwise you would not have it weightless?
Well, okay, so there's a lower bound of n for this general transformation.
You just restate the question.
Okay, so I think the question was, can we potentially do better, right? Or do we what do we lose, right? If I wanna reduce the space. In order to have the properties that I stated, weight freedom and constant time, I need at least linear. This would at least be an n, okay? But I don't know. So there's a gap between the lower bound and the upper bound. Okay. And so if we have this general transformation, and sort of this beats already all previous attempts to implement multi-word registers from single-word registers. Pretty much all previous results were only single-writer, and in terms of step complexity, they were also worse. So this is what I want to talk about, is this transformation. And the first. And I told you that this is really a memory reclamation technique that we use here, because this is the workshop, what the workshop is about. So I'll start with a solution that uses an unbounded amount of memory. Okay, and then I will show you how we can reclaim some of that memory. And the idea is that every process has an infinite number of these sequentially writable objects available. Okay, and they can just put them in use whenever they want. And then there's a global pointer which points to one of those objects, and that's the object that I want to work with. And that pointer can change, and wherever it points to, we call that the sequentially writable object that's currently in use. And so if a process wants to execute an operation from, on an object, it just reads the pointer and then executes on the pointer on whatever object that pointer is pointing to. If a process now wants to overwrite the value, all that process does, it chooses one of its own objects from its own pool, it writes the value there, whatever value it wants to write, and then it changes the value of the pointer so that the pointer points to the object that this process wanted to write. It's pretty easy, right? I mean, that's kind of a very standard technique. And so when we write the pointer, that's the linearization point. And why is this linearizable? Essentially, let's say object O2 is in use from here to here, and at this point, the pointer gets overwritten with a new object. there are all these processes that sort of read the pointer with value O2 and then they execute their operations. Even if they execute their operations somewhere here, they can still linearize in that interval, right? Because they read the pointer at some point in time. That's when the object was in use, and then we can just linearize all the operations on that object whenever that object was in use. And yes?
How do you keep everything the same, right? I go to my own, it's not the same as the GenF where the pointer is pointing, or when I change something, I change all of the copies?
No, you only change one copy, and then you swing the pointer so that it points to your copy. Let's say now there's still some processes. Let's say the pointer first pointed to one of my copies, and let's say Kirk reads that pointer and wants to perform an operation. Then the pointer changes to your copy. Kirk is still performing an operation on an outdated copy, but that is okay because, well, you know, maybe he does it here, the pointer has already changed to the new object, but the operation will linearize in this interval. Okay, the operation will linearize before it, and this is kind of special for the write operation. A write operation overrides whatever changes Kirk makes.
Can you move to the previous slide?
Yeah.
So each one has his own copy.
Yeah.
Once something happened, it's not updated anymore, right?
That's right. Well, so let's say you want to write V. So this is me. Okay, this is Philip.
I want to write 3.
Okay.
Kirk wants to write 4.
Let's say not write, and because if he writes, that's the easy case. Let's say he wants to execute an operation on that object. Okay, and he reads pointer while it's still pointing here. Okay. Now you write 4. So what you do is you write the 4 into a new object. You change the pointer. And now Kirk is still playing around with this one. That's fine in terms of linearizability because it linearizes at the point in time. It will linearize in the past when it was still pointing here. Yeah. Okay. So this is a kind of pretty easy. The only downside is, of course, that we need infinite amount of memory. Oh, sorry. Yeah.
What if you and Kirk both want to increase the value by 1? So as you read it, you plus 1.
Right. Okay. So we are both here, and we are both reading the pointer while it's still pointing there.
Yeah.
Okay. So let's say we do a fetch and add on there. Then first Kirk does a fetch and add. Let's say the value is 3. Kirk does a fetch and add, changes it to 4. I change it to 5. But all of that may happen after Eris has already written 10 in there and changed the pointer. But that's fine because the linearization order would be Kirk increments it from 3 to 4. I increment it from 4 to 5. And then it gets overwritten with 10. And even though maybe our fetch and increments happen here, because the interval of execution is so far in the past, we are allowed to linearize them here. I hope did this answer the question? Is it? Yeah. Okay. This is just how linearizability is defined. It needs to look like the operation took effect at some point in time during my execution interval. Even though I do something that is kind of weird here, I can always assume it took effect there. Yeah.
Will the change of the pointer be the serialization part of that?
The change of the pointer is the linearization point of the write operation. But the execute operation linearizes maybe some point in time during the interval. I don't really know where it linearizes. In the worst case, I just linearize it just before here. I mean, all the execute operations kind of don't really do anything until after. I just linearize them just before the write. And then it looks as if those operations, and immediately got overwritten with something else. Okay. So now we have infinite space and we would like to bound the space. Okay, and what we want to do is we want to use linear space per process. Okay, so just a linear number of these sequentially writable objects for each process, and that's where the quadratic space in the end comes from. And so now instead of choosing a new object that hasn't been used before, I need to choose an object that may have been used before. And so what I want is I want to use an object that's currently not in use. It shouldn't be pointed to at this point in time. And I need to make sure that no process accesses this object again until it's being put back into use, or so there's this interval. Currently, the pointer doesn't point to it, and nobody's allowed to do anything with that object until the pointer points to that object again. That's the property that I want. I'll brush over this. So this is somehow the property that we need. And how do we achieve this? We'll use an announce array, and that allows us to say, okay, we're protecting this object from being used. And so what a process does when it wants to execute its operation, it reads the pointer, it gets an object, and then it announces it. It writes into its announce array, saying, I'm currently reading this object. Please do not recycle that object or write to it or anything. And a writer will scan the announce array, and it will choose an object which is currently not announced, and it's not in use. Okay, the pointer is not allowed to point to. And the fact that every process has n of these objects ensures that we can always find such a thing. But then we need to be careful, and this is exactly what Aris was talking about earlier in his talk, because what could happen is that essentially before before I announced it, some process has already put it back into use, right? So I read it, I fell asleep for a really long time, and now some other process uses the object or starts writing it, and then I announce it's kind of too late, right? So what I want to do is I want to read the pointer again, and I want to make sure that the pointer hasn't changed. And only if the pointer hasn't changed, I'm allowed to perform the operation on the object. Or if the pointer has changed, then I have to start over, okay? And that's that's sort of where lock freedom comes from, and this is really pretty much what you get with hazard pointers or these memory reclamation techniques. So the goal of this talk is, as I said, so here with this, because we start over, it could happen that an execute operation keeps, starves. Okay, a process can never finish it because every time it reads the pointer twice, the pointer will have changed. We want to make this wait free. And so instead of starting over, we have to do something else. And the idea is that we kind of, instead of executing the operation on O equal O prime, we will try and find a different object that we can also perform the operation on. And this needs to be an object that was in use at some point in time. So the idea is that the process that writes provides a hint to the process who's executing something. Okay, and that hint is essentially saying, oh, I'll perform a lot of write operation. Instead of performing your operation on O, here's another object that you can perform your operation on. And then what we need to guarantee is that this hint must have been in use at some point in time during the execution of this. And no operation can overlap with the sequential write. Let me just show this by a picture here. So the idea is essentially something like this. Let's say this is the pointer, and I am putting O into the object O, write that into the pointer, put that into use. Okay? And then I perform a lot of additional write operations. Let's say n additional write operations. Then, and there's also Kirk and Aris there. With every write operation, I'm putting a new object into use. And then what I'm going to do is I'm going to tell Kirk and say, look, I just put this object into use. And then I'm going to tell Aris, look, I just put this object into use. And if you guys keep failing, if you can't use the object that you read from pointer because it changes, then you will have gotten a hint from me that gives, where you see, okay, well, there's another object that was in use at some point in time, and then I can perform my operation on that one. Okay, so I know we're late for time, so I will skip over that. Now, all of that has linear step complexity because essentially just scanning the announce array takes a linear number of steps. However, the work for scanning the announce array can be distributed over n write operations, and that allows us to achieve constant step complexity, where every write operation actually just takes constant number of steps. Okay, now, if you thought this was difficult, we'll take it a step further. I have talked about linearizability as the correctness condition of choice. And our implementation is linearizability, and that was the state of the art. However, I told you also that if I have linearizability is so useful. Why? Because if somebody gives me linearizable objects, I can assume they are atomic. But that only applies to deterministic algorithms. If I use randomized algorithms, it's not true. Okay? Then linearizability is just not enough. And so there's another correctness condition which is called strong linearizability, which is sufficient for randomized algorithms. And that is essentially the same as linearizability, except that linearization points of the past cannot change in the future. So if you have an execution up to this point in time for a stack, and you extend that execution, the linearization points that have already happened are not allowed to change anymore. And if you think about what we have just discussed earlier, this is exactly what we have been doing in this algorithm. We've been changing past linearization points a lot. First I should say, so if I have randomized algorithms and I schedule them with something that's called a strong adaptive adversary, then strong linearizability is the correctness condition that you want. Now, you remember this picture that we have talked about quite a bit earlier. What happened in this picture was that a process, let's say this green process, read the pointer here, okay? But only here it performed this operation on the object. And that was okay, because only here then, okay, so once it performed its operation here, it would just linearize in the past, okay? But let's say there are these two processes. What was the example earlier? Kirk performs a fetch and add, or increments a counter from 3 to 4, and I increment a counter from 4 to 5. If I do my increment before Kirk, then our linearization order has to change, right? But we are using an object that's already not in use anymore, and so essentially the order of our linearization is only determined after, so we decide on our linearization order after it has already happened, okay? So linearization points from the past are affected by the future, and strong linearizability does not allow that. Okay, and so I think in the interest of time, I will just show you this slide. So the problem is this memory reclamation technique that I have shown you and it's been used in a lot of work is kind of inherently not strongly linearizable. And so this is what the Pozzi paper from last year was about, applying essentially this technique in order to achieve strong linearizability. And we did this for something that's called load-linked store conditional. So there's a lot of work on, essentially you can think of load-linked store conditional. It's like a compare and swap object, but it doesn't suffer from the ABA problem. And there has been a lot of work on linearizable load-linked store conditional because it's an extremely useful primitive, but none of that work is strongly linearizable. And this algorithm at Pozzi last year is the first strongly linearizable algorithm. And it essentially uses a similar technique as I've shown you before. It just gets more complicated. Okay, so go to the conclusion. So this technique that is weight-free, it has several linearizable applications I haven't talked about in various papers. But none of those techniques typically achieve strong linearizability. Also hazard pointers, or even if you have lock freedom and you use any of those standard lock-free techniques, you do not preserve strong linearizability. And this is much harder, and I think it's an important question to find memory reclamation techniques that apply to strong linearizability. Yeah, that's it.
Take time for at least a few questions here.
Yeah.
So I'm not sure why does hazard pointer do strong linearizability?
It's exactly the same problem. What you typically do with a hazard pointer is, so you read something, then you set the hazard pointer, and then you read it again, right? Now, if you have a match, then you linearize at the point in time when you, if you have, essentially, if you have a match, you need to linearize in the past. You need to linearize at the point in time that the pointer was pointing to the object.
You could linearize at the second read, right?
No, you can. In general, you cannot.
Okay, we can take
Yeah.
So just for those of us who are not experts in this audience, like the strong linearizability, like I understood linearizability to be there are some points where, right? But I don't quite know what it means to be like the future can't affect where you can linearize with that. Like somehow that doesn't make as much sense to me.
So many data structures have this property where you have two concurrent operations, okay? And at some point in time, the operation may or may not linearize. But whether it linearizes at this point will only be decided much later, okay? And this is not allowed with strong linearizability. Essentially, with strong linearizability, as an outside observer, you should be able to pass through the execution and at any point in time say, oh, this linearizes now, this linearizes now, this linearizes now. And if you go in the future, nothing can change that anymore. And what was you were using Harris' list, right? I think. I believe that's also not strongly linearizable, for example. I had a student look into that. Yeah.
So the strong linearizability is the right notion of concurrency for
randomized
for
algorithms.
randomized
Yes.
adaptive adversaries.
Exactly.
For oblivious adversaries, is it the same as deterministic?
Very good question. For essentially, there's nothing known if you don't use the strong adaptive adversary. There's no good correctness condition that we can use which preserves the power of the adversary if you replace the atomic object with implemented objects. And for the oblivious adversary, for example, you can prove that no good correctness condition can exist. I mean, essentially, there's nothing feasible, or it would be so strong that it's not useful to achieve that. So it's really, we really only understand the strong adaptive adversary at this point. That's also a very interesting research question, I think.
All right, let's thank the speakers again. There's a reception out. Hopefully there's a reception out.
Was it true in time, or is it?
You did a very good job at